Tonight what we are going to be talking about is atomic structure, and with this, how to calculate the average atomic mass, meaning the average mass of all of the various isotopes of a given element in the universe, and then also to figure out the percent abundance of these, which means we're trying to figure out what is the percent of hydrogen 1 in the world out of all the hydrogens. So it's a very basic formula, which is right up here. And to figure out the average atomic mass. This is an extremely simple formula. All you have to do is take each individual percent and multiply by its mass, okay? And then keep going. If there's like 3 isotopes, you just keep going. 4 isotopes, keep going. And then you divide that answer by 100, and then you get your average atomic mass, so the average mass of all of them. All right, so let's try to do an example problem. The element gallium has 2 stable isotopes, gallium-69 and gallium-71. 69 has a molar mass of this. If I give you a more specific molar mass than just gallium-69, you are going to want to use that. And then it says gallium-71 has this molar mass. I want to make that a different color. I'll do purple. And then gallium-69 has a relative abundance of 60.11%, and gallium-71 has a relative abundance of 39.89%. So what that actually means is that if I had a little baggie of all the galliums in the universe, 60% of the time I would be able to get gallium-69, and then 39 or 40% of them I would be getting gallium-71. So how do we do this? All you have to do is you take 68, so the mass, and you can take mass times the percent or percent times the mass. The key is that you need to make sure that you align the correct mass with its correct percent. 68.9256 grams per mole times its percent, which is 60.11%. Then we are going to add the next guy of the next isotope. So that would be 70.9247 grams per mole. And don't worry about these units. We're going to get into that next semester. Just write them right down right now. Times its percent, so 39.89%. And all you have to do is put that into your calculator, divide that by 100. Personally, what I would do is do the numerator, press enter, and then divide everything by 100. And that way you don't really have to worry about the correct use of parentheses and orders of operation as much. And so you end up getting 69.73. For these, I would like you guys to round to the nearest hundredth position, and the unit would be grams per mole. Percent abundance. There are 2 types of percent abundance formulas that we're going to be using. There is a traditional one where you only have 2 isotopes, and then there is a more complex, challenging one, which will be on the next slide, and that will be with more than 2 isotopes. When you only have 2 isotopes, what you're going to do is you are going to take the mass of isotope A, and it doesn't matter which one you define as isotope A as long as you remember which one it is, times X, which is what you're going to solve for, and that's its percent, plus mass of isotope B times 100 minus X. And what you're trying to do with this guy right here with the 100 minus X is you're really multiplying it by its percent abundance, which with 2 is either, when you have 2 isotopes together they equal 100, so mass of isotope, the percent of isotope B has to be 100 minus the X, because isotope A has the percent of X, and then that equals the average atomic mass. The average atomic mass is going to be given to you in these problems. So in this case you have to solve for X, which is your percentage. So once again, it doesn't matter which one I define as isotope A, I am just going to say whichever one comes first, typically is what I do. So what you're going to do is mass of isotope A, so I'm going to plug in 1.007 times X plus my mass of isotope B, which is given to me as 2.014 times 100 minus X, all over 100, equals my average atomic mass, which is 1.00784. And now, as long as you can solve for X, you can do it whichever way you want. Personally, I'm going to start distributing and multiplying out as fast as possible. So I'm going to multiply both sides by 100, and I get 100.784 to get that denominator off of the left. And then I'm also going to distribute out these numbers. So it's 1.007x plus 201.4 minus 2.014x. Okay, and now I'm going to condense to get the like terms together, so it's negative 1.007x. I'm going to subtract that 201.4 from both sides, so I get negative 100.616. Divide both sides by a negative 1.007, and I get my x equals 99.92%. So what I want to do now is make sure I know which one was the 99.2, and I'm going to look at where I assigned x, and I assigned x with that mass of hydrogen 1. So hydrogen 1 has a percent of 99.92%. So 99.9% of the time I would grab a hydrogen 1 isotope. And then how do I figure out hydrogen 2? All I'm going to do is 100 minus that 99.92, and we end up getting 0.08%. Now for the challenging one, and what this is 3 or more isotopes. Can almost guarantee you're going to see one of these on your test, especially in the written section. So silicon has 3 naturally occurring isotopes, silicon 28, 29, 30. So right away I know that I have 3 isotopes, so it's going to be a little bit more challenging. If the average atomic mass is 28.086 and silicon 29 has a natural abundance of 4.67, what are the natural abundances of 28 and 30? So what will always happen with these challenging ones is that we still won't only provide you with 2 of the percentages, we will always provide you with that 3rd or 4th one, and we will also provide you with the average atomic mass, but you're going to have to set it up a little bit differently. It's a little bit more challenging. So the first thing that we're going to do is I'm going to fill in my formula. So the mass of isotope A in this case is 28, and I'm going to multiply by x plus mass of isotope B. In this case, I'm just going to go in numerical order. So my isotope B is going to be actually silicon 29. The interesting thing about silicon 29, whoops, I don't want to do that. The interesting thing about silicon 29 is that I actually do know its percentage. So I'm just going to take the mass and I'm going to multiply it by its percentage. Now I'm going to keep going. So plus the mass of isotope B, and now I'm going to work on this guy, I guess. Mass of isotope B times the unknown. So these 2 guys up here are the unknowns, and then this addition plus dot 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 will be always your knowns. I'm just kind of going in a different order because I'm going by mass as opposed to the general formula order. So my 3rd one is the one that I don't know, and so that would be silicon 30, which is going to be 30, and I'm going to take 100 minus x minus the other percentages that I know. So minus, in this case, 4.67. And that is going to equal my average atomic mass, which is 28.086. All of that we need to then divide by 100. So what I'm going to do right away is I'm going to start to distribute, and I'm going to try to distribute it out so it's as easy as possible for me to then get like terms together. So I've got 28x plus 135.43, and that comes from the 29 times 4.67, plus 3,000 minus 30x minus 140.1 equals 2,080 or 2,008.6. Okay, then I'm going to start keeping like terms together. So negative 2x plus 2,995.33 equals the 2,808.6. Subtract the 2,995 from each side, so 2x equals negative 186.73. Divide by negative 2, and you get 93.37. Now I need to figure out which one that goes with, and if I look at where I've defined x as, that would be silicon 28. So I know that silicon 28 has a percent abundance of 93.37. Silicon 29, we already were given, that is going to be 4.67. And then silicon 30 is easy to solve. I can either put it in here and do 100 minus the 93.37 minus 4.67, or I can figure out what numbers really you're just trying to add up to 100. So what number adds up to 100 with the 4.67 and the 93.37, and I get 1.96%. A way to check this then is you use that average atomic mass formula where you take the percent times the abundance, divide by 100, blah, blah, blah. So I could take this 28 times 93.37 plus 29 times 4.67 plus 30 times 1.96. Divide that by 100, and I should get my average mass of 28.086. If you do not get that, then you know somewhere either your math went wrong or you're using the wrong formula, so you need to redo it.